I had made a poll about 3 months from now where I had asked for some video ideas, and you guys seemed to like the idea to discover Earth 2.0 from all the other ones. But since then, I have been quite lazy, and at making this video, it took a lot of time. But finally, I was determined to publish content and get some real TRP down the line. A few weeks ago, I had discovered NASA's website once again, and yeah, this is not to see their new missions, but it was to appreciate the fact that they discovered over 5,000 exoplanets. But have you ever wondered, upon all these planets, how many of them are actually habitable, or shall I say, near about habitable? Well, I have spent some nights on caffeine to scrap the entire website down and get only the required topics into a CSV file. Let's open it. So basically, I have chosen some specific criteria on which we will judge the planets and eliminate them if they don't meet up the expectations. Let's list it out, and these are the criteria that I want to filter with: gravitational acceleration, type of planet, orbital radius, orbital time period, Goldilocks zone, and planet speed and radius. And for the entire dataset, we will use these columns to get the data from: light years from Earth, planet mass, stellar magnitude, planet type, orbital radius, and orbital velocity. These columns contain enough data to calculate all the criteria needed, and of course, planet name. It is not a criteria, but we will use it to see the final results. Okay, let's try to view the dataset that we have, and I want to see the heading and the first row of the data only. That way, we will know that we are working with the right dataset. Cool, so that's the first two rows of the entire dataset, and now we can move on further. This list variable named planet data rows will contain all the required data for us along the entire project. Okay, so let's try to filter some data. Firstly, I will calculate gravitational acceleration for each planet. Our Earth has something around 9.8 meter per second square. But let's see how other planets behave. For that, let's take up a look at the column number 7 and 3. This contains the scales of planet radius and mass. But hold up, they are in the scales of Jupiter or Earth, and some are even unknown. We gotta fix that. According to physics, Jupiter is actually equal to 317.8 times the mass of Earth, and Jupiter's radius is equal to 11.2 times the radius of Earth. So if we iterate into the list of planets, firstly we check that if there is an unknown data entry. If so, we remove it. Next, if we have a valid data, we split it into two parts. It is easy, see, if we have a value like 1.21 x Jupiter, then we can use the x as the pivot for splitting the data. The 0th index after the split will contain the numeric value, and the first index contains the word Jupiter. With this concept, if we see the word Jupiter, then we multiply the data by 317.8 to get it to the Earth scale. And if we see it, the word Earth, we just leave it as it is. Next, we shift to the column 7 and check if we have a valid planet radius data entry. If we encounter an unknown data entry, we remove it. And if we have a valid data entry, we split it into two parts, just as we did before. And if it is in Jupiter type scale, we multiply the data by 11.2, and for the Earth type scale, we just leave it as it is. Good, we have an uniform scale of planet radius and mass now. Let's do something fancy. We can calculate gravitational acceleration of each planet. School taught me that the mass of Earth is around 5.972 in 10 to the power of 24 kilograms, and the radius of Earth is around 6,371,000 meters. So according to Newton, gravitational acceleration of any planet is given by multiplying the gravitational constant with the mass of the planet divided by the square of the radius. Okay, enough physics now. Let's code. Create 3 empty lists to have planet mass, radius, and names. We append the data to the list from the dataset and respective columns. We iterate through the list and enumerate into the gravitational acceleration formula. Then we put the obtained value of gravity into an empty list. That's awesome. Now we multiply the data by the mass of the Earth and the radius of the Earth. Why exactly? Well, see, if there is a value like 2.21 into Earth radius, it means that 2.21 times the radius of Earth. So to get the integral value, we need to actually multiply the real value of the Earth radius to the original value that we got. So according to physicists, we humans can survive up to 10 times the gravitational acceleration of Earth. And technically, we can sustain a gravitational acceleration of about 100 meter per second square. Let's iterate the list and find the number of planets having gravitational acceleration less than 100 meter per second square, and then we print the length of it. Okay, the output says that we get around 3,951 planets. Great. Now let's try to see how many different types of planets we have. If we look at our dataset in column 5, we can see planet types. Let's check how many different types of planet we have. We make a new list for planets, then we iterate through the dataset and pass output through our set function so that we do not have any duplicacies. Okay, we have 4 types of planets, namely gas giants, Neptune-like, super-Earth and terrestrial. Now to be honest, I don't really care about the gas giants and Neptune-like planets because they are far from survival. Let's focus on the super-Earth and terrestrial category. We make an empty list again, and for the suitable planet type, we iterate through the list of planets and peep into the 6th index of the list and check if the planet type is terrestrial or super-Earth. If we find any matches, we append them to the new filter list, and finally we print the length of the new list. Oh god damn, we are just left with 1452 planets which are close to our survival. I will now check how many planets are fit in terms of orbital radius and orbital time period, since this will affect atmosphere, heat receipt from the sun, and we would like something really close by to that of the Earth. First, for the orbital period. Take a look at column 7 in the dataset. The data given are in the form of years and days, and some are even unknown. So all are mixed. We need to make something uniform. We have made a new list and peep into the column 7 which contains the orbital time period. We iterate through the dataset, and if we find a data with an unknown value, we remove it. And if we find a valid data, we again split it into 2 parts like we did before and check if the scale is in the form of days or years. If we encounter a year scale, then we multiply the data with 365 to transform it to day scale, and if we encounter a day scale, then as usual, we leave it as it is. I will now check how many planets come into the category of Goldilocks zone. Oh, by the way, according to NASA, the Goldilocks zone or habitable zone is the range of distance with the right temperature for water to remain liquid, and mathematically, a planet in the Goldilocks scale of 0.38 to 2 is in the safe range to survival. So we make another empty list. We then iterate through the list of existing planets and peep into the data given in column 11 and check it if it is in the range of 0.38 and 2. We remove planets which are not in the Goldilocks zone, and then we print the length of the existing planets. Well, we have come a long way. We have just left with 25 planets in the output, and these planets are really close to our survival. Time for the final check. Amongst these 5,000 planets, how many planets have suitable planet orbital velocity? Now, scientifically speaking, we human cannot take any orbital velocity greater than 200 km per second. Therefore, to calculate orbital velocity, we need 2 things: orbital circumference and time. For the distance or the orbital circumference, we have to calculate the circumference of the orbit, that is by 2 pi r, and we know where we will get the radius from, that is from the column 7. Finally, we multiply the data by 1.496 into 10 to the power of 9, which will bring the data to kilometer scale from astronomical units. Then we create a new list of planet speeds and iterate through the existing planets in a list. To calculate the orbital time in seconds, we multiply the orbital time period by 86,400, since 1 day is equal to 86,400 seconds, and the velocity of the planet equals to the orbital distance divided by the time taken in the scale of kilometers per second. And we need to remove any planets which has more than 200 km per second of orbital velocity, since that is beyond the human survival. Now we need to print the length of the entire list which we have obtained. Wow, we are only left with 8 planets which have survival orbital velocity. That is fun. But now we have come this far, we have come to 2 major conclusions. But let's take a moment and summarize what we have done so far. We took the entire collection of NASA's exoplanets. We kept filtering dataset based on acceptable gravitational acceleration, planet type, distance from sun, orbital velocity, and currently we have rejected 5,502 planets in total, which does not meet the required criteria for human survival. Now we are left with 2 major conclusions: the list of 25 planets which are within the Goldilocks zone, and the list of 8 planets which can support the required orbital velocity. Now let's make a final comparison and merge these 2 lists to find out the top planets which can support life in terms of physical conditions. We make a final list of habitable planets, then we merge these 2 lists together and print both the length and the contents of it. And here we go, only 6, the top 6 planets among the all 5,535 exoplanets which can actually support life in terms of physical conditions. And surprisingly, all these planets are of super Earth category. If you wondered about the source code of this entire video, then you must check out my Patreon and get hands on the entire code with explanations with just $1. and this is how I found Earth 2.0 using data science.